Uh, any questions about anything we talked about last time before I get into this? All right. I think I'm ready now to say what the exam on Thursday is going to be about. So exam 2, the topics are going to be rigid body, free body diagrams, rigid body statics, and centroids. And so I think we'll get a little farther than this before Thursday, but this is all that's going to be on the exam, just these sets of practice problems. And then Thursday, tomorrow or Thursday, I'll post the first problem set. It's going to be, I like this kind of problem. It's going to be something to the effect, I have to think about the details a little more, but it's going to be something like write your own single problem that incorporates these things. So you have to think about how to incorporate things. It's sort of an exercise in knowing like what the limitations are on what we're capable of solving. Oh, write the problem and then solve it, you know. So yeah, you have to solve it. So you're kind of trying to make it as simple as you can probably, and so the restrictions on what types of joints you can have on a single body and still do calculations with it, and what kind of centroid calculations you can do, those sort of all, you have to sort of keep those in mind as you design the problem. Can we design these? You don't get as many points if you do that. But it'll be due in a week. You'll have like a week to work on it. All right, so the first just mini topic I want to talk about is equipoulan systems. Some books have full chapters. I think all books probably have full chapters on this. Many classes put a lot of detail into studying this. I'm not going to put as much detail into it. But the idea is this. In a rigid body, and the rigid body part is key, and I'll go into that in a second. There are different combinations of loads that are statically, or this is also true in dynamic cases. It still has to be a rigid body, but dynamically equivalent. And so, for example, no matter what combination of loads a rigid body has acting on it, you can replace those loads with a force vector at a chosen location and a couple, and still have the behavior of the rigid body be exactly the same. So without changing the behavior of the rigid body. I'm not going to go into how to calculate that. It's not difficult to figure out or anything, but I think it's sort of cool that that's true, but I don't think it's really that useful. But I want to, so what if it's not a rigid body? What if it's a deformable body like we use in deform? So what if it's a deformable body? Then consider an object with a force here, and a force here. Okay. That is going to, so what's this body going to do under these loads? It can deform, so it's going to bend in here, it's going to bend in there, right? It's going to deform based on what these loads are, right? And there's no way to apply, so say that you want to come up with an equipolant system of loads where you have a force vector at this point and a couple. There's no way to come up with a force vector applied at this point and a couple that's going to make it deform in this way. Okay, so when things deform, there's no equivalent to equipolant systems. The one thing that we are going to use so one equipolant force idea that we will use and that is that in a rigid body, you can move any force along its line of action without changing the behavior. So, for example, if this is a rigid body and a force is applied here, you can move that force anywhere along this line and the behavior is going to be the same. So you can move the force anywhere along the dotted line. Yeah, the couple thing. Well, the way this works, it has to do with the about point. The idea is, so what the cross product does when you calculate the moment is basically it figures out how far the force is perpendicularly, how far the line of action of the force is from the about point perpendicularly. And so no matter where you move this force along the line of action, if you took that cross product, you'd get the same thing. That's the reason that it works. Because you're still just this distance from the line of action, from the about point. Again, notice that, so I said no equipoulan system stuff works when you're talking about deformable body mechanics. And if you think about moving a force on a deformable body, the same is true here, right? This force would pull a little bubble out of the bottom of this if it was deformable. If you move this force up to the top, it would push a little indent into the top. Those are different. So this only works for rigid bodies. And then that makes even, yeah, right. Oh, so, okay. It's confusing if your physics needs to make sense, But mathematically, yeah, you can, mathematically, if you want to say that this force acts on this body down here at the, below where my screen is, and it's along that line of action, it's not going to mess up any of your calculations. It doesn't make much sense. I suppose you could imagine this as being an invisible, rigid protrusion on both sides. And so the force is like acting on some invisible thing that's rigidly connected to it. Let me do a quick example to show how this works. So let's say that this person this is the new fitness craze. Actually, it is. It's like planking, except he's okay, he's holding onto a handle that's connected to a roller. It's like a very uncomfortable way to paint the wall. Okay, so touching the floor there, and this roller's touching the wall there. And I just have this as a roller so that, because we know how to treat that joint. This we'll assume is a friction contact. And you can imagine this would get hard after a while, so should probably draw some sweat droplets. Just to be thorough, yeah. He's probably wearing some kind of wrestling singlet, I suppose. Okay, so yeah. So let's say that the center of mass, okay, when we talk about centroids, we're going to talk a lot about center of mass. Something interesting about the center of mass of an object is it doesn't actually have to be on the material of the object at all. So if you measured the center of mass of this person, it would probably be here somewhere in space. All that means is you have, well, it means, so what part of this person does gravity really pull on? We said that it pulls on the center of mass. What part does it really pull on? Does gravity calculate the center of mass? No, it pulls on every part, right? So really what you're doing when you're applying the weight force at the center of mass is you're saying there's an equipoulan system that instead of applying infinitely many infinitesimal weight forces, applies a single finite weight force at the center of mass. And the center of mass is just where you can apply that finite force and have it be equipoulan. So what do we need to know? Let's say that we know this distance is 0.5 meters. And let's say that we know this distance is 0.8 meters. Question? Possibly. Or leaning over really far. His really long arms. I don't know. So what we don't know is we don't know how far it is from the foot to the wall horizontally. That seems like a problem. And we don't know how high the center of mass is. Okay, that seems like a problem. But let's go through this, write out the table, and we'll see that we can do this calculation, because the reason we can is that without changing anything, we can move these forces, the point where these forces act, anywhere along their lines of action. Okay, so we can choose any value we want. So free body diagram. Looks like, okay, we'll take some liberties on this one. So there's the person. There is a force going. Okay, you probably want to do this thing again where you move this over a little bit. So the force coming from the wall, this is a roller, so what direction is the force going here? It's, yeah, perpendicular to the wall. So this way, I'll call that RB. And then the weight force is acting here. Again, it's not on the body. That seems a little odd, but you can imagine that that's connected rigidly by some invisible connection. Then it makes plenty of sense. The weight is, oh, well, I have to give his mass. I think I said, what would that be? 80 kilograms. So the weight is 784.8 newtons. And then this is a friction contact. So what kind of force do we have at the foot? What? Yeah, right. So I'll call this RA. And then the table. Let's put the coordinate system here. And that is a slightly easier place than other places to put the about point. So I'm going to put the about point at the origin. Okay, so the force at the foot is acting at the origin. The about point is the origin. So the row vector for RA is 0. The force vector is RA with 2 components. And since rho is 0, the cross product here is 0. And now we'll go to the weight force. Well, what's the point? What's the location where the weight force is applied? We know that the x component is positive 0.5, but what about the y component? Well, the line of action is this, so you can move it up or down all you want without changing anything. So I'm going to put it at 0. Just because it's on the line of action. You could put it at h, I suppose, too, either way. Yeah, let's put it at h. I like that. Good idea. The about point is this. The row vector then is 0.5 h. The force vector is 0, negative 784.8. And so now you can see how that line of action thing works. When we take the cross product, we have 0.5 times negative 784 minus h times 0. And so that h just doesn't come into the calculation. And so you end up with negative 392.4. And the same thing is going to happen with the horizontal location of this roller. So I'll call that W for width because we don't know the x coordinate. We do know the y coordinate is 0.8 positive. The about point is the origin. The row vector is W, 0.8. The force vector is negative RB, 0. And so the cross product, you can see again that W doesn't come into it, and you end up with minus 0.8 RB. What? Positive, yeah, sorry. And so Newton's second law says RAX, RAY plus 0, negative 784.8 plus negative RB 0 is equal to zeros. The rotational equation says negative 392.4 plus 0.8 RB is equal to 0. That's 3 equations for 3 unknowns. And if you solve it, you get RA is the vector 490.5, 784.8, and RB is 490.5. Any questions about that? So that's supposed to be just sort of an illustration of why it doesn't change the math to move the force along its line of action. And you can always do that. Unless the body's deformable, then you have to, but you can always do it anytime you're treating a body as a rigid body. All right, and then the last thing I want to say, this is really quick, and then I guess we'll just take the break and then start centroids when we come back. Statically indeterminate systems is the name for a system where you can't solve for the forces just using statics. It turns out you can solve these, but we're not going to do it in this class. In D-form, we'll learn how to do that. So this is any system where the forces can't be found using just statics. And the way that presents itself is you have more variables than equations. And if you want to get picky about it, it's not just the number of equations you have, it's the number of linearly independent equations. Okay, so here's an example. Say you have a cantilever beam that in the middle is supported by a roller. And then you have like a force acting down here. This is statically indeterminate. And you can see that if you go to the free body diagram. So what are the loads applied by a fixed joint? There's a force vector and a couple. Yep. And what are the loads applied by a roller? Yep. So that's going to be this way. Call that RB. So we have 1, 2, 3, 4 variables. We know that in 2 dimensions, Newton's laws give us 3 useful equations. And so we have 4 variables, 3 equations, and we can't solve it. That's a little unsatisfying, right? Because you know that if you took an object like this out of whatever material it was, welded it to the wall, put a roller here. First, I mean, nothing crazy would happen, you know, like it wouldn't break because it's statically indeterminate. And not only that, statically indeterminate means that there's infinitely many combinations of, you know, infinitely many solutions to the problem. And it's not like, I mean, you know, intuitively, it's not like it's going to toggle between these different solutions. If you measured the loads at these different places, they'd be consistent. They'd stay whatever they started as. Well, it turns out that you can solve problems like this, but you have to take the deformation of the material into account. And so we could solve this using the methods of deform if we knew how much this beam deflected under a given load, how much this roller was compressed under a given load. We could take those things into account and calculate these. But for statics, if you see a problem like this where you can't come up with enough equations, then we're just done with it. Okay. One way to sort of eyeball it is notice that a statically indeterminate system is one where you could always take away some amount of support and it would still be static. Okay, so like in this case, this would still be static if we took away this roller. Or it would still be static if we replace this fixed joint with a pin joint. And so we know, thinking about it that way, that it's statically indeterminate. It's over constrained. Yep. Yeah, normally we would. I just didn't draw it in there. But yeah, the weight would be in here. Sometimes we'll see that there are problems where we neglect the weight just because the other loads are so much bigger than the weight that it doesn't really change the answer very much. Any other questions? Okay, let's come back at 2:07 and I'll get started with centroids.